Problem number 24. Solution for this problem you can find below this video in the reference. A uniform circular disk of radius r begins with the mass big M about an axis through the center of the disk and perpendicular to the plane of the disk. The moment of inertia is I0 equal 1/2 mr square. A hole is cut in the disk as shown in the diagram. In terms of the radius r and the mass m of the original disk, what is the moment of inertia of the resulting object about the axis shown? Solution. So first we can represent full moment of inertia of this disk, this whole disk, like this. I0, that's our original moment of inertia, 1/2 mr square. I1, this is the part of this disk with the hole, and the I2, that's the moment of inertia of this part around the center of original disk. So now we need to count what is I2 to find what is I1. Using a parallel axis theorem, we can find that I2 equal 1/2 mr square plus mr square, where m small, that's the mass of our this new small disk, and the small r, that's the radius of this small disk. But m small equal m big over 4, and the small radius equal big radius over 2. So this is how to count what is I2 in terms of big M and the big R. That will be this expression: 3/32 big M big R square. And finally we can count what is I1 of this part of disk with the hole. That will be 1/2 minus 3/32, which is 13/32 mr square, which is correct answer B. Problem number 25. Solution for this problem you can find below this video on the reference. Spaceman Fred's spaceship, which has a negligible mass, is in an elliptical orbit about planet Bob. The minimum distance between the spaceship and the planet is r. The maximum distance between the spaceship and the planet is 2r. At the point of maximum distance, Spaceman Fred is traveling at speed v0. He then fires his thrusters so that he enters a circular orbit of radius 2r. What is his new speed? Solution. Of course, we can solve this problem using regular energy conservation and angular momentum conservation in this problem. So first we can find what is the speed of for circular orbit of this spaceship. This is just a regular formula you can get from equation that force of gravity equal to centripetal force, and after that we can write equations for angular momentum conservation and energy conservation. Here v0, that's speed in the furthest point, original speed, and v1, that's speed of the spaceship in the closest point. After that we can express v1 through v0 put it in this equation, find what is V0 in terms of G m over R, and use this expression. But this is the long way. We can do a shortcut. We can write equation for total energy, which is kinetic energy minus gravitational potential energy for circular orbit, and that will be negative 1/2 Gmm over radius, which is in our case 2r. But this formula actually could work not only for circular orbits, but also for any elliptical orbit. Let's rewrite it. So total energy for elliptical orbit equal negative 1/2 Gmm over A, where A it's the size of big semi-axis of this ellipses. That could be proved by calculations, but we can use this as our exceptional knowledge. And now we can just write simple equations. First, we already found that v square equal Gm over 2r, where v is our speed we need to find. But for elliptical orbit, we have total energy equal negative 1/2 Gmm over 3/2 of big R, half of this big axis. But from the other hand, that's equal to kinetic energy in this furthest point plus potential gravity energy. And from here we can find what is V0 square. So from this formula we can find that V0 square equal 1/3 Gm over R, and using this expression for V square, we have that it's equal to 2/3 V square. And from here we can find that the V equal just square root from 3/2 of V0, which is correct answer A.